Today we will be talking about AMGM, APGP, and the corresponding inequalities and the equalities. So what we're going to learn here today, the basic idea is that there's specific sequences. So the number one question that should come to your mind is that what is a sequence? A sequence is a function that means, in other words, you have 1, 2, dot, 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 n, or till infinity, and you want to assign. Can you accept the students? Can you assign you want to assign a real number to each and every one of this 1, 2, right? So for 1, you want to assign a1, for 2, you want to assign a2, and dot, dot, dot. So this is nothing, but if you observe, it's nothing but a function from the natural numbers, which we call n, to the real numbers. So to put it mathematically, a sequence is a function from the natural number set to a real number set. An example. So since it's a function, it's really easy to understand, easy to write it down because we are very familiar with functions from our school days. So you can write f of n is a function. It's like you can say 2 of n squared, or 2 of n to the power 9, or n into n minus 3. You can do various things out there. Or you can also say e to the power n, or something like this. So this is what a sequence is all about. Okay, it's a function from natural numbers to real numbers. I gave an idea that you're mapping each and every single element of the natural numbers to a real number, and you have seen some examples. But the entire goal of sequence, that part you will be learning, there are two folds, two questions mainly. One is finding spatial sequences, and two is, which is not in your syllabus, but you will learn it when you go into CMI, is finding the limiting behavior of the sequence, like what happens in the long term, which is harder, but more fun. Okay, finding spatial sequence or spatial properties of the sequence. So what we're gonna do here is this one, not this one. Finding spatial sequences. So spatial sequences means it has some properties. It has some relationship. So how do you define a sequence? So sequence can be defined in two ways, mostly. One is writing down the function itself, like 2n squared, like this. So we call it analytical form. And another is called recursion form. This recursion idea will again come over and over again in this course. But the recursion form's idea is it also will come in theory when you are doing induction and stuff like that. Also, it will come in the programming aspect. So recursion. So let's say f of n is equal to 2n squared, or 2n, or 3n, like this. It's a specific analytical mathematical format. Okay. And recursion is where you cannot find a mathematical format. So you have all heard about probably Fibonacci series, right? An is equal to, or an plus 1 is equal to an plus an minus 1, where it starts with two numbers. But do you guys know what is the final analytical form of an? Do you guys know that? So let me try to show it to you so that you understand. Just give me a minute. Let me start sharing my screen here. So what does it mean? It means that everything has an analytical form, but it's very hard to find. If you try to find it, it's actually not really easy to find it. Okay, it needs advanced mathematics. But it turns out that you cannot always find the analytical form of a function. So that's why you need a recurrence relationship, where you understand the dynamics of how one sequence element is interacting with the next sequence elements. Usually this is referred when it's a sequential growth. Let's say you can model a stock pricing with this manner. Like you can say that like it will grow based on what is today's price. You do not want to know about the previous prices. Just an example. Similarly, for Fibonacci series, you know that it was developed from rabbits, right? How rabbits reproduced. So that was dependent on the previous generation and the two generations before. So that's how the n and n minus 1 comes in. So, but they do not know what's the final equation. So that's the basic idea. So recurrence is nothing but a relationship between a few sequence elements in general, and that gives you kind of a general overview of how the function is going to work. This is easier to code and program rather than the analytical form, and it's hard to find analytical form here. So there are two specific methods of finding spatial sequences. So here, today we will be learning about three special sequences. Number one, what we call arithmetic progression. Number two, geometric progression. Number three, harmonic progression. Okay, so this is three different progressions, and we will learn both of their analytical form, and I will see whether harmonic progression has an analytical form, or we will be learning it, probably given you as a homework. And the second is recurrence form. So this is your first insight and your first interaction of how to transform a recurrence form into analytical form. And this will be used over and over again in your problem solving sessions. Okay, it's very important. Okay, so let's now first start arithmetic progression. Arithmetic progression, the basic idea is that, let me give you an example, that if you start with two numbers, let's say geometrically, if you start here, let's say at some C point, you hop over, you get C plus D. Now, if D is negative, then you go to the other side. Again, you hop over, you get C plus 2D, and this goes on, right? And this makes sense because everything, so for example, whereas usually the sequence, now many people want to understand, and it's very important to understand that why are we learning all of this? So first of all, sequences mostly come in time series data. Okay, if you want to connect it to the data science aspect, time series data, because it's A1, A2, dot, 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 AN. So it's like the 1, 2, these are time series, the time stamps. You are seeing the data. So for example, arithmetic progression is a very simple sequence of saying that something with time is increasing at the same rate, or something in time is decreasing at the same rate. This is what arithmetic sequence tells you. Okay, we will see one interesting thing. So this is regarding more philosophy about life, that everything in life usually follows something. For example, if you see our height, they do not, they, yes, it follows a linear pattern, but after some time it stables. So with time, it's like kind of this, it stables down, it kind of become constant after a certain time, right? For money and other physical things, again, it just increases, and then there's a point of inflection and it closes, because there's something called compounding. That's why I believe geometric progression is very, very important, and it's very visible in real life, because that's how things multiply. So geometric distribution, progression, you will see that things multiply at a certain rate. That's the basic idea of geometric progression. However, arithmetic progression is kind of a local behavior, short-term behavior. But anyway, so we are assuming, but that's a good price. Usually, they are linearly progressing. So in arithmetic progression, things increase step by step, right? So what we wanted to promise, that we want to know what is the nth expression. What does it look like? And we also want to know, how does the Tn related to the previous Tn minus 1 or Tn minus 2? How are they related? So the first one is the analytical form. The second one is the recurrence form. And they have a delicate interplay between them happening. Okay. So I personally love 2 because it's more fun and it's easier. I always love easier things. The final goal is Tn, but you will see how number 2 helps in Tn, finding Tn. But since you have said that you want number 1 mostly, let me do number 1 first without doing the number 2. So we'll start with A. It hops to A plus D in the first step. So if we call this, again, we see the notation T naught. Okay, we call this A1. Okay. So A2 is A1 plus D. So this is A1 again. We call it A1. Then this becomes A2. And then this becomes A1 plus 2D. This becomes A3, right? And then this becomes A2 plus A1 plus 3D. This becomes A4. So if you go to AN, how many hops will be there? N minus 1. Because for going to 2, there is 1 hop. Because if you essentially it's N minus 1, because from 1 you're going to N minus 1 steps. Jumps you should have, and jumps are not 1, the jumps are proportional to D. So therefore at N, you need to take N minus 1 hops, and you start from A1. So it's A1 plus N minus 1D. Okay. And that's what Tn is all about, the final term. This is the arithmetic thing. And then comes the arithmetic final term, and then comes the six recurrence relationship. So what is a recurrence relationship? So to understand, this is one of the most beautiful part, because finding recurrences occur more. It's like dark matter and white matter in the, not white matter, but dark matter in the universe. Dark matter is more because it's infinite. It's what we see in non-dark matter, that is something we can perceive. Now what we cannot perceive is infinite, right? Similarly here, the recurrence relationships are infinite. It's like a dark matter, we don't know. We only can write the equations of things that we know, and that's where the fun happens. That's why it's easier to write down a recurrence relation rather than a full, as I have said, full analytical expression, and that's why it's fun too. So can someone tell me that to understand, to write in the recurrence relation, you have to find out one single process that is happening, right? So can you tell me what is the process that is happening? How can you write it down mathematically? So yeah, any process that is happening constantly, that is staying invariant over time or over every movement, that is how you build a new recurrence relationship. Let's say you want to model something in your life, in some real life situation. So here the hopping is constant. How do you model the hopping? What is hopping? So essentially it's nothing but how do you model the hopping. So this distance is that means the consecutive difference tn minus 1 is d. Simple. And it starts from the T1 is A1. Now, can I use this? So now this is something of the process, and this is something we have found in a different way, right? This is a recurrence relationship. This is an analytical relationship. Now, can I go from here to here? Let's say someone gave you this relationship. Can you go from here to here? That's what we learn now. How to express a recurrence relationship into analytical form. It's good if you can find out in this manner. So in this, you see that Tn is equal to, so let's try out simple things. So Tn, so T1 is equal to A1, T2 is equal to, you can see if you move to the other hand side, or you can say T2 minus T1 is equal to D, T3 minus T2 is equal to D, dot, Tn minus 1 is equal to D. And this is something called telescopic sum. So observe that if you add on the left hand side, you have A1 and you have n minus 1D. So this is the first equation, second equation, and the n equation. So in the last n minus 1, you have n minus 1D. And in this, if you sum it up, you will see that all this cancels, only T and m. This is so beautiful and elegant, right? This is equivalent to this.